This is the theorem of change of a scale in Z transformation. So we have to change the scale in Z transformation by this theorem. Now the theorem states that if Z transformation of the sequence f of k equals to, this is the Z transformation of Z equals to this sequence function, then this Z transformation of a to the power a k f of k, that means this a will be the scale actually, scale, and this effect of a will this scale will affect the Z transformation with this. That means this equals to Z transformation of Z by a. Okay, this is the Z transform of what? Z by a. That means this a will affect the transformation of Z. Now we are given fz equals to Z transformation of f of k. This can be written as a sum of minus infinity to plus infinity with the by the definition of Z transformation f of k. We have discussed it in the previous lecture. F of k z to the power minus k. Now substituting z by a for z, just using z for z by a, then we get the z transformation of f. Z by a transformation will be this equals to minus infinity to plus infinity f of a. Okay, and in replace of z in the definition we use z by a only. So this will be z transformation of a to the power k f of k, excuse me, but the Z transformation of a to the power k f of k. This is the actual sequence taking L together with a to the power k. This Z transformation of this can be written as minus summation minus infinity to k equals to minus infinity to plus infinity a to the power k f of k. This is the whole function of z and z to the power minus k. By using the same definition of Z transformation, f of k, in replace of f of k, we have used what? A k f of k. Okay, just replacing this, then we can write f of k into a to the power k, and z to the power minus k can be taken as L together z by a to the power minus a k minus k. Now from 1 and 2 we found that this equals to, actually these two results are same. That means this equals to this, hence the theorem. That means the change of scale will be affect the transformation of Z. This is the required proof. Now example, find the Z transformation of a to the power k. If you want to find out the Z transformation of k a to the power k, where k must be non-negative, that means negative cannot be negative. So we know that Z transformation of 1 equals to Z divided by Z minus 1. From example 12, we have done this example. Z transformation of 1, what will be? From by the definition, we have found this result, Z divided by Z minus 1. Now for the given sequence, by the scale of change formula, actually we can overlook the example 12. Example 12 where actually this is the example 12. Okay, the transformation of discrete unit uk equals to 1, and 1 for k greater equal to 0 and 0 k less than 0. Therefore Z transformation of this uk, by the definition of Z transformation, here the limit of k what will be? 0 to infinity. Okay, uk, this function, sequence function uk z to the power minus k, it can be written as like this, 1 plus z to the power minus 1 z, just putting the value of k, and uk will be what? Only 1. Okay, uk equal to what? Only 1 for these values, non-zero values of k. This can be written as, after putting 0, z to the power 0 equals to 1, z to the power minus 1, z to the power minus 2 minus 3 up to infinity. Okay, Now this is actually geometric progression, geometric series to infinity, and we must know about the sum of this series will be divided by 1 minus r. A is the first term, r is the common ratio. Hmm. R is the common ratio of this series. This is the geometric series actually. So after putting the values of a means first term, and r means the common ratio. Common ratio what? Second term divided by first term, or second term divided by third term divided by second term, or fourth term divided by third term. This why this will be identical 1 by z r values. This equals to actually this, and we are using this result. Okay, z transformation of 1, z transformation of 1, we found this result z divided by z minus 1. So in the change of scale, now example in 23, z transformation of 1, we must know z divided by z minus 1 from the above example 12. For the given sequence, by the scale change formula, z transformation of a to the power k into 1, what will be the result? Z by a. Okay, for this a to the power k, the z will transform to z by a. Okay, by the this theorem. Okay, a to the for this introduce a to the power k, z will transform to z by a. This is why if you introduce a to the power k, then this will be z by a. Z will be transformed to what? Z by a. Now this can be written as, after taking LCM in denominator, we get this z divided by z minus. Now from example 24, similar process, find the z transformation of c to the power k sin alpha k, c to the power k sin alpha. But we already known from example 13, from example 13 sin alpha k, the transformation of sin alpha k, we have to proceed from this example. Okay, we have to start from this example, z to the transformation of sin alpha k, using definition of z transformation. We have found this sum in previous class. Okay, in previous class we found this sum, and using this sum we are testing the change of a scale in z transformation. Okay, by using the theorem. Now now we will use this. Need to explain this? Hello, need to explain this one? This is the previous lecture. Now I am using this result only, but you have to start from this first to last. Okay, now using this one in example 24, just the transformation of alpha k will be this one by above example 13. Now applying the formula of change of a scale, that means applying the theorem of change of a scale, we get c to the power k sin alpha k. That means this is the scales c to the power k, and this will transform the z transformation to z by a. Okay, but this will be c, this is why z by c. Z will transform to what? Z by c. Understand? Just this c, for introducing c to the power k, we have to change in the transformation of z by z by c. Okay, just this will be the result. Now again another theorem, shifting property. Shifting theorem. If z transformation of f of k is this, that means if this is the z transformation, then z transformation of f of k plus minus 1 n, k plus minus n, that means this is also a sequence, will give the result z to the power plus minus n. That means this z main sequence of z transformation, z to the power plus minus n. This means this will give the power on plus minus n of the z transformation of f. That means this is multiplied, this z transformation of z transformation of z will be the give the result multiplying with what? Z to the power plus minus n. This is the actually shifting property. Now we'll prove this property for different case. Actually there will be used two case and very important theorem in z transformation. The theorem reads states that z transformation of this equals to this. We have to prove this one. Now consider z transformation of this sequence equals to can be written according to the definition of Z transformation. K equals to minus infinity to plus infinity, f of k plus minus n z to the power minus k. This equals to z to the power plus minus n, z to the power plus minus n into summation k equals to minus infinity to plus infinity, f of k k plus minus n into z to the power will be also k plus minus n. That means we have taken the by the using Z transformation formula. Okay, just if you introduce Z plus minus 1 here, but here z to the power minus k into z to the power plus minus n, another one, just minus, just this one plus, so this will be cancelled if we take z to the power this and this, so plus minus n will be cancelled. So this is the extra part for me. So if we take this z to the power plus minus n in the first one, in the first way, so we have to write the z, this z, how, z to the power minus k plus minus n. That means another plus minus n, this plus minus n will be balance the term. So this equals to z to the power plus minus n. This can be written as minus infinity to plus infinity. Just k plus minus n equals to what? R. Substituting with R, we get f of r into z to the power minus r. Okay. Now this equals to plus z to the power plus minus n, z to the power plus minus n f of z. This is the actually what's this one? Actually, this is the definition of Z transformation. So this is the, also we can write f of z, that means Z transformation of z. So this is the actually proof of our theorem. Now for the case 1, this equals to this will be for case non-negative. For k is non-negative, that means k greater or equal to 0. The transformation of this equals to f of k plus 1 z to the power minus, according to the definition of what? Z transformation. Now z to the power n, taking z to the power n for non-negative, we can write z to the power minus k plus n. Just only taking positive n. Then for put r equals to k plus n, then putting r equals to k plus n. Okay. Now z to the power n f of r dr, k plus n equals to r. Then z to the power n f of r dr. This is also this equals to f of r z to the power minus r. Now z to the power n r equals to this total summation n equals to infinity. But we can write this 0 to infinity and another one r equals to 0 to n minus 1. N minus 1, making this summation into two parts. Okay, if we take 0 to infinity, then if we subtract 0 to n minus 1, then we get n to infinity. Okay, n to infinity. N to infinity can be written as 0 to infinity minus 0 to n minus 1. Okay, this is why this summation divided into two parts. One is 0 to infinity, another is 0 to n minus 1. That means values of r divided into two parts. Now z to the power n, this is the by the definition of z transformation, we can write this equals to f of z. So minus z to the power n, this is also can be written as like this, r equals to 0 to n minus 1 f of r z to the power n. Now z to the power n, z to the z transformation minus r equals to 0 to n minus 1 f of r z to the power, what will be n minus r, z to the power n minus r. Actually, this will be the result for what? For k greater or equal to 0. Similarly, for case 2, we can write, if we input k minus n, okay, k minus n, and this is the k plus n. Similar process proceeding in this way, k minus n, with this k minus n, we get z to the power minus n, r equals to minus n to infinity. R equals to what will be? Minus n to infinity for z to the power minus r. And this can be written as like this. This infinity, this summation can be divided into two parts. One is 0 to infinity plus minus n to minus 1. Minus n to minus 1. That means less than 0 what? Minus 1. Minus 1 to minus n. And this total make the total summation r equals to minus n to infinity. So we can write this in two parts. First part is this r equals to 0 to infinity, and other part is less than 0. That means minus n to minus 1. This. Then this is also by the definition of z transformation, z to the power minus n f of z. Now this can be written as this. For r equals to minus m, we can write this one. So this is for the second case, using just negative sign, and this is using just plus n. These two case is the result for shifting property, because r equals to plus minus n. First one is k plus n, and second case is and k minus n. This is the whole theorem. Okay, you have to prove this. You can make corollary from these two theorems. If the f of k is the sequence, then f of k minus n is this by the theorem we get, but f of minus 1, minus 2, minus 3 dot dot minus n up to this will be 0. Transformation of this will be 0. Similar for other sequence, f of k minus 1, k plus 2, 1, k plus 2, this will be the 0. Actually, this is produced from the main theorem, our main shifting theorem, and those are the corollary. Now another theorem, if f of k is the sequence, that means this is the z transformation of this, and this is the z transformation of this, capital Z, then a or b are also constant, then the inverse z transformation of this will be a into z transformation, inverse z transformation of this, individual inverse. Okay, taking individual inverse, sum of taking individual inverse of z transformation will be equal. Now we can prove the z transformation of this whole f of k plus b z of k. This is the whole sequence. The transformation of this equals to this. Just taking a into z transformation of k plus b into z transformation of zk. So we can write this one. Similarly, for inverse one, for inverse function, we can write also a into f of k. That means this can be written this, replacing. Okay, now this replacing what? Z of k. This is the actual inverse by using properties of inverse function. Now it can be written as a into f of k sequence, b into zk sequence. Now this is also the inverse of what? In z inverse f of z, and this is also inverse of z inverse. Actually, only two lines. Now we'll start inverse z transformation. Okay, inverse z transformation. Find in the sequence f of k and f of z is defined as the inverse z transform. Finding the sequence f of k from this. This is the actually z transformation. Okay, finding this sequence from the z transformation called inverse z transformation. It is denoted by z inverse. Inverse z transformation of z equals to f of k. Actually, this is the main definition of inverse z transformation. Now find the inverse z transformation of this. Consider z transformation of this is this. Okay, this is actually z transformation. Now if we consider dividing by z, here we get what? 2 by z, right? 1 minus 2 by z, 1 minus 2 by z. So if we consider 2 by z modulus of 2 by z, that means absolute value of 2 by z less than 1. And if we draw a circle with radius this, radius half, radius will be what? Actually, this is it can be draw a circle with radius maybe square root 2. This will be the circle actually, and this condition will be 2 by z absolute value less than 1. So f of z can be written as taking z common. Taking z common in denominator, we can write 1 divided by 1 minus 2 by z. Okay, 2 by z means 2 into z inverse. 2 into z to the power minus 1. So this is also 1 by z. 1 by z means z to the power minus 1, and this can be written as 1 minus 2 into z to the power minus 1 to the power minus 1. Okay, this is whole power minus 1. Now this series, this is the actually a polynomial series, z to the power minus 1, 1 minus x to the power minus 1 formula, 1 plus twice x plus x square, 1 plus x square plus in this way, 1 plus x to the power minus 1 minus x to the power minus 1 formula, what, 1 plus x square plus x to the power cube dot dot infinity. Okay, now z to the power minus 1 multiplying, then you get this. So f of k, this sequence can be written as 2 to the power k minus 1, 2 to the power k minus 1 for k equals to 1, for k equals to 1, 2 to the power 0. Okay, that means first term will be what? First term will be what? 2 to the power 0. For k equals to 2, this will be only 2. For k equals to 3, 2 square. In this way, we get the sequence will be what? 2 to the power k minus 1. Now, if z by 2, that means divided by 2, this we get z by 2. If z by 2 less than 1, then we can write after taking minus 2 common. After taking minus 2 common, 1 divided by 1 minus z by 2. Then minus half, then 1 minus z by 2 to the power minus 1. This is also another sequence, series of 1 minus x to the power minus 1. That means 1 plus x square plus dot dot. All will be plus. So in this case, the sequence can be written as minus 2 to the power k minus 1. Okay, the sequence can be written as minus 1 to the power k minus 1. Actually, the inverse transformation can only be settled when region of convergence is given. So this is actually our required inverse transformation. Now another example of Z transformation, inverse Z transformation. Solve the difference equation. We have to solve this equation. Actually, this is the sequence equation: yk plus 1 minus 2 into yk minus 1 equals to 0, and condition for k greater or equal to 1. That means k is non-negative. So, and another initial value given y0 equals to 1. Okay, we have to solve this equation. This is the actually difference equation. We have to solve this equation by the help of Z transformation and inverse Z transformation. Now solution, this equals to 0 given. Now taking Z transform on both sides of this one. This is the equation number 1, given 1. Now taking Z transform, that means Z transform is of this sequence, okay, equals to 0. Now individually taken Z transform of this minus 2 into Z transform of this equals to 0. So this can be written as Z into YZ, capital YZ, minus Z into YK plus 1 minus 2 into Z transform of this equals to 0. Now if we write the by the definition of Z transformation, Z into YZ minus Y naught Z minus 2YZ equals to 0. For K plus, for K is non-negative, remember it. Now from this line, actually Y naught equals to what? 1. Using this condition, we get Z into YZ minus Y naught Z. Only Z can be written as Y naught Z because Y naught equals to 1, minus 2 into YZ. YZ taking common, then Z minus 2 YZ minus Z. Y naught means what? 1. This Y only Z. Now YZ equals to, this is the Z divided by Z minus 2. So actually this YZ equals to what? This is the inverse of the sequence what? YK. YK is the main sequence. YK. this sequence equals to what will be z inverse z transformation of this. Okay, if we get only sequence, then this will give the inverse z transformation of this. Inverse z transformation of this will be the our required sequence. This equals to inverse z transform of this what? This can be written as, after taking z common, 1 divided 1 minus 2z inverse, just as look like before example. Z inverse z transformation of this is the actually series of what? 1 minus x to the 1 minus 1 polynomial in x. X means what? 2 into z to the power minus 1. That means 1 plus x square plus x cube plus x3 will never be finished up to infinity. So x means what here? 2 into z to the power minus 1. Just using this one. Now the transformation of this series equals to actually what? 2 to the power k, right? Just in just the coefficient of the whole series will be what? 2 to the power k. K for what? K is greater or equal to 0. For k equals to 0, we get first one. For k equals to 1, we get these two. That means inverse of z to the power minus 1 coefficient, and z to the power minus 2 coefficient what? For z equals, for k equals to 2. That means 2 squared. This is the actually what? This is the sequence equals to this. We have solved yk. Just we have found the solution for yk by using inverse z transformation. Now multiplication by k, another theorem. If z transformation of the sequence f of k is this, then if we multiply k with this sequence, will give the result minus z into ddz. This is the operator, differential operator of the complex function z, ddz of Fourier z transformation of this. So we can prove this. Now this left hand side equals to z transformation of this k into just multiplying with the constant k. Then this can be written by the definition of z transformation, k equals to minus infinity to plus infinity, just sequence this sequence and z to the power minus k by the definition of what? Z transformation. Now minus z, taking minus z, this sequence can be written as z to the power minus k minus 1. Okay, just changing this power, we can take minus z here just before summation, minus z into k equals to minus infinity to infinity minus k f of k z to the power minus k minus 1, and then minus z equals to just taking minus k and z all together in a bracket, then we get this one. Now this equals to k equals to minus infinity to plus infinity f of k, and this is the actually what? X to the power n formula of differentiation. Okay, n into x to the power n minus 1, n equals to what? Minus n, right? This can be written as ddz of z to the power minus k. That means differentiation of z to the power minus k with respect to z, right? This is the formula of this. So this is the differentiation of z to the power minus k with respect to z. Remember it. So minus z equals to, this can be written as summation minus infinity to plus infinity f of k z to the power minus k. That means differentiation of this can be taken, because this is with respect to z only, all other z will be constant. So this equals to minus z into ddz of f of z. Okay, now in general, if we replace k by k to the power n, okay, in generally in this theorem, if we have multiplied just k, but if you replace this k with the k to the power n, then this will be what? Up to n times order of differentiation. This is the order of differentiation actually. How many differentiate we have to? We have to differentiate n times. This is the n times differentiation, and this is the z transformation. Okay, now if the sequence is f of k is 1, that means the sequence f of k equals to 1, then the transformation of 1 will be what? This we must know. We have found this from by example 12 in the previous lecture. Now putting these values in the above theorem, we get that transformation of k sequence can be written as minus z ddz, and this z transformation will be what? 1 minus z to the power minus 1 to the power minus 1. Actually, this is the polynomial of z to the power minus 1. So minus this can be written as like this. Just taking differentiation, x to the power n different and what? N into x to the power n minus 1. There will be minus 1 minus 1. This is minus 2. Again differentiation z to the power minus 1, because this is not actual x. Okay. Now differentiation of z to the power minus 1 with respect to z, what will be? 1 by z square. 1 by z square minus 1 by z square. 1 by x formula what? Minus 1 by x square. Differentiation of 1 by x what? Minus 1 by x square. But here we are differentiating z 1 minus z to the power minus 1 to the power minus 1. This is why this look like what? X to the power minus 1. So the differentiation of this with respect to z can be written as this. And again we have to differentiate because this is not actual x to the power minus 1. So z to the power minus 1, again differentiation will be minus 1 by z square, and this minus will be cancelled with this plus. So this altogether can be written as this. Now for the second corollary, if f of k equals to 1, then the transformation of 1 can be written as this. Okay, this equals to what? Z transformation of this one, z by z1, by using example 12 as the previous example. So if we substitute n for 2, then k square, okay, n equals to 2, substituting in the theorem z to the power transformation of k 2 can be written as just order, and order will be what? 2 in this theorem, minus z ddz to the power what will be? N. N means what here? 2. So this can, and the transformation of f of z in the place of f of z will be this. So by using the theorem we get this term for k for n equals to 2. Now this can be written as 2 times. Okay, actually this is the second order. This is why, and this z divided by z minus 1. Now minus z ddz can be written as, this can be written as actually u divided by b formula. Okay, u divided by b formula differentiation what? B square in denominator b square, and b into ddx of u minus u into ddx of b, right? Okay, and this is the minus z, this minus z, and minus z into can be written as minus z digit, and this after calculation we can we get from this third bracket z divided by z minus 1 whole square. So it is another u by b process. Okay, another u by b process. So this differentiation can be written as b square. B square means what? This square in denominator, this square, and b into, b means what? This one, b into ddx of u minus, there will be minus u into ddx of b. Okay, u by b process just. Then after calculation we get this one. So for the second order n equals to 2, we get this result. This is very important for you. Now another theorem for the division by k. The theorem states z transformation of k equals to, if this, then the z transformation of the sequence f of k divided by k, thus dividing with by k, will give the result minus integration with respect to z, z to the power minus 1 f of z dz. Understand? Actually this is the statement of the theorem we have to prove. Now you are proving. Try to understand concentratedly. Z transformation of this, actually this is the left hand side, f of k divided by k. This is the division by k theorem. So f of k divided by k, this is the actual sequence. It can be written as by the definition of Z transformation. Our previous lecture, from our previous lecture, we defined this k equals to minus infinity to plus infinity. The just f of this sequence into Z to the power minus k by the definition of what? Z transformation. This equals to k equals to minus infinity to plus infinity f of k. This k and Z to the power minus k can be written as within first bracket 1 by k into Z to the power minus k. So taking a minus sign, k equals to minus infinity to plus infinity f of k. This is the integration of what? Z to the power minus k minus 1. This can be written as integration of this. How? Integration of this what? Actually, x to the power n formula, if we apply x to the power n formula, then we can write Z to the power minus k minus 1 plus 1 divided by minus k minus 1 plus 1. That means 1 will be cancelled and k will be in last, and there will be a minus. This is why a negative sign. Minus minus will be balanced. Then we get only positive value. Understand? This integration, what's the will be the value? This one. So actually this is the integration with respect to z. This is why this z used. So equals to, this is the integral of k equals to minus infinity to plus infinity f of k z to the power minus k minus 1. And this equals to minus integration of z to the power minus 1. We can found z to the power minus 1 from this power. So f of k z to the power minus k. According to the definition of z transformation, L2 this whole term can be written as f of z, because this equals to f of z. Okay, this is the definition of z transformation. So our theorem, this equals to can be written as minus z to the power minus n z transformation of z dz. Understand? Very interesting. Now initial value theorem. If the z transformation of f of k is this, for k is non-negative, then the function, if we take functional value 0, f of 0 equals to limit z tends to infinity of the z transformation. We have to prove this. Actually, this is the initial value theorem. Proof z transformation of this by the definition of z transformation, k equals to 0 to infinity, because k starting with 0. K is non-negative. This is why we have to take limit of k with 0 to infinity. Now, if k equals to 0 to infinity, f of k z to the minus k is the actually definition of z transformation. So this summation can be written as f of 0 plus f of 1 z inverse. After putting the values k equals to 0, we get f of 0. Okay. If k equals to 1, then second one. If k equals to 2, then third. In this way, whole series can be written as equals to f of z. So if we taking limit z tends to infinity on both sides, if you taking limit z to the power z to infinity, z tends to infinity. So if z tends to infinity, 1 by z what will be? 0. 1 by infinity what? 0. This is why. And z to the power minus 2 will be also 0. Every term will be vanished up to infinity. Okay. If we take this z to infinity, so for very large of z, all terms will be vanished except first term. This is why f of 0 will be limit and z tends to infinity of this. This is the actually very easy theorem. Similarly, final value theorem. The final value theorem can be states limit k tends to infinity, f of k equals to limit z tends to 1, z minus 1 f of z. This is the final value theorem. Now, if we take the z transformation of the sequence this minus this, f of k plus 1 minus f of k, this can be written, this is the whole sequence, second bracket. Remember that every sequence can be represented by second bracket. So this whole one is the sequence, f of k plus 1 minus f of k, second bracket. So by the z transformation definition of z transformation, k equals to 0 to infinity, this whole sequence z to the power minus k. Z to the power minus k always multiplied with the function, because This by the definition of Z transformation. You can follow the first lecture. Now Z into f of z minus f of 0 minus f of z equals to limit and tends to infinity. Taking limit up to and tends to infinity from both term, we can write k equals to 0 to n f of k plus 1 minus f of k z to the power minus k z to the power minus k. Okay, z to the power minus k. Limit z tends to 1, z minus 1. This can be written as, actually if we put 1 in the place of z, 1 minus 1 will be 0. This is the f of 0 plus limit z tends to 1 from this 2 f of z taking common, we get z minus 1. Okay, and f of 0 will be in right hand side, then f of 0 plus this one. So by changing the order of limits, we get changing the order of limit, z tends to infinity 1, z minus 1, f of z, this is f of 0, limit changing, just limit changing, limit and tends to infinity limit first, then summation, after summation this will limit z tends to 1 and this series. Now limit and tends to infinity, this is the wholly can be written as f of 0 plus summation this, by putting the value of summation. Okay, f of 0 z tends to infinity, z tends to 1, z limit of this equals to this summation k equals to 0 to n f of k plus 1 minus f of k. Now if we take the limit and up to infinity, then f of 0, this is also another 0, because after putting k equals to 0 there is another 0, f of 0 minus f of 0, f of 1 minus f of 1, f of 2 minus f of 2. In this way all term will be vanished except this one. Okay, limit and tends to infinity f of n plus 1 only will be exist. This term, this and this will be cancelled. So this equals to what will be limit and tends to infinity f of n. Okay, f of n. So this equals to limit k tends to infinity f of n equals to, this will be the f of k, just replacing n by k. Now this is the final limit k tends to infinity f of k, the final value theorem proved. Now a very important theorem, a convolution theorem for Z transformation, very important theorem for you. Let us consider two sequence f of k and z of k, individual two sequence, and the convolution of these two be sk. Okay, can be denoted by sk, another sequence with these two convolution of these two sequence will give in identical sequence sk, another sequence where sk can be written as n equals to minus infinity to plus infinity f of n z of k minus n. Actually this also can be written as n equals to minus infinity to plus infinity f of n, f can be changed to z and this z can be taken as f. Actually this is and this identical, and this is also can be written as f of k and z of k and zk and f of k also. Actually this is the convolution form of these two sequence. Now we have to prove these two. Actually we have proved this theorem, convolution theorem, in Laplace transformation and in Fourier transformation also, but it has in Z transformation. So this theorem has many contribution to the transformation, because it started in different kinds of transformation, Laplace transformation, Fourier transformation, and in at last Z transformation, and it has many uses in engineering. This is why it has started in different kinds of transformation. Now proof is very small, little. A Z transform of 1, that means 1 means this one. This is actually convolution theorem statement. Z transform of this one can be written as Z transformate of ASK. ASK is the composite transformation. ASK, okay? Composite of what? These two sequences, f of k and z of k. The transformation of this ASK can be written as by the definition of the transformation, k equals to minus infinity to plus infinity, then first bracket. This is the actually ASK equals to what? And equals to minus infinity to plus infinity, f of n and z k minus n. This can equals to and equals to minus infinity to plus infinity, the first summation, and second summation is this f of n z of k minus n into z to the power minus k. And this two summation can be used like this: f of n into z to the power minus n and z into k minus n into the z to the power minus k minus n. Okay, here another z to the power n. So z to the power n and z to the power minus n will be what? 1, will be balanced. This is why we can take this composite summation into two individual summation. Now this n equals to minus infinity to plus infinity, f of n z to the power minus n into this will be the what? Z transformation of this z. Okay, so this is also the Z transformation of f of n. So f of z into z of z, actually composite transformation. This is proved. Convolution property of causal sequence, f of z equals to this and z of z will be this, starting from 0 to infinity. Okay, from non-zero n. Now if you take f of z into z of z, multiplication, that means composite form of the two sequences f of z and z of z. This will be f of 0, f of 1, z inverse. This multiply with what? And this one. Now taking multiplication, we get f0 z0 plus f1 z0, f0 z1, z inverse. In this way, this is the another sequence actually. So this can be written as this is the h0, this is the h1, this is the h2, in this way. That means this is the composite Z transformation of ASK altogether. So Z transformation of ASK can be written as Z transformation of this. This is the convolution form. Now example 27, evaluate the Z transform of the sequence f of k equals to 0 to infinity 2 to the power k, and another one k equals to 0 to infinity 3 to the power k. This is the whole represented by the sequence f of k. Now you have to find out the Z transform of this sequence. Now Z transform of this 2 to the power k. After putting k equals to 0, 0, just using k equals to 0, 1, 2, 3, we get this sequence. And this is the polynomial of x. Look like x means what? 2 into z to the power minus 1. Okay, this can be written as 1 divided by 1 minus x. This is the infinite series. Okay, infinite series, sum of infinite series what? A divided by 1 minus r. R is the common ratio. So we can write first term means a equals to 1 divided by 1 minus r. R means common ratio. Common ratio means second term divided by first term, third term divided by second term, like this. Similarly, Z transformation of 3 to the power k can be written as 1 by first term divided by 1 minus 3. This is the also common ratio. You have to First of all, write down this series like this for 3 to the power k. Okay, then we can find out the sum of infinite series. Now f of z transformation of f of k will be z transformation of these two individual series by actually this is by convolution theorem. Okay, now this is the product of two z transformation individually. This is the z transformation of 2 to the power k, and this is also the z transformation of what, 3 to the power k. So just taking multiplication we get this. This is the actually result. Okay, you will try 1 to 5 at home. This will be the homework for you.